All right, RC circuits. All that means is they have a resistor and a capacitor. That's really all it means. So let's draw a circuit with a resistor and a capacitor, and a battery. There's our EMF coming up here, everything's fine. Resistor there, and capacitor there, which looks dangerously like a battery. So when the two bars are the same length, it's a capacitor. And also when you write a C next to it, it's a capacitor. Okay, so let's apply Kirchhoff's rules to this thing. Well, there's no junctions in it, so we're just going to apply the loop rule. By the way, Kirchhoff, I have a conspiracy theory about Kirchhoff. I'm pretty sure Kirchhoff and Walt Whitman were the same person, so look into it. Okay, we're going to apply the loop rule. The first thing we have to do is define our current direction, like that. And for the loop rule, we want to define our loop direction. I like to go clockwise, because that's the kind of guy I am. Okay, so we go around. Let's start here. I'm a test charge. I'm moving along. I'm moving with the resistor, with the current, so it's minus IR. Okay, and now I get to the capacitor. Well, what's the potential drop across a capacitor? It's not necessarily related to current, it's related to charge, right? CV equals Q, or let's see, the delta V across a capacitor is the charge on its plates divided by the capacitance. So to get the sign right, let's really think about what's going on. I'm a test charge. If the current is flowing this way, that is going to charge up this capacitor plate positive. And if that capacitor current flows on there to make that positive, it's going to suck negative charge onto this plate from this side of the battery. And that's okay, because if you suck negative charge going this way, that's really a current going that way. So it really is current going this way everywhere. So if the current flows like that, this is the high potential side, this is the low potential side. If I'm a test charge and I go from here to here, I'm going down in potential. It's kind of like the resistor. So from the low potential minus the high potential is negative. So it is a negative potential, and it is not the current, it's the charge. I'm just going to write that as Q. It's Q over C. Okay, and let's just keep going. I am a test charge, and when I go across the battery from the low to the high side, then that is plus EMF equals 0. Okay, so there is our equation. Now we have a problem. Usually the point of a problem like this is you want to solve for the current, but now we can't really solve for the current because we have the current here, and this is R is known, C is known, the EMF is known, but we have the charge there, and those are two different functions. So we need to relate them somehow. Well, the key is that we have the same current in the resistor and charging the capacitor. Okay? Whatever current flows here through this resistor is also building up charge there. If that current is building up charge on that capacitor, then we do know one thing. We know that current is the time rate of change of the charge. We know if there's a current going through here, that's in amps, that's in coulombs per second. That's how many coulombs per second are building up on the capacitor. So we do actually have an equation to relate these two things. So what we're going to do is, instead of writing this in terms of I and Q, current and charge, we're going to write it just in terms of charge, because we can replace this I with dq dt. Okay? So let's do that. So let's see. So that's minus IR. So that's going to be minus R dq dt minus Q over C plus EMF equals 0. And now we have to solve that. And now this is big. I never warned you about this. I warned you about vector calculus. I didn't warn you that this is a differential equation. Oh, we have to do differential equations here. And don't worry, I'll show you how to do them. It's all sort of just guesswork and silliness, okay? But one thing before we get into this differential equation to realize is that Q is a function. of time. Okay? Your hint is there's a dq dt there. And what this means is this circuit doesn't just have a constant current flow. This is a circuit whose the only solution to Kirchhoff's loop rule is for things to change in time. So this is a dynamic circuit. It's still a DC circuit because even though the current and the current changes in time, it always goes one direction. So it's not really an AC circuit yet, but it's not sitting just with a constant current at all times. Okay? So step one in solving this differential equation, usually the first thing you want to do is get the differential part by itself. So let's just write it real quick. We're going to bring this over here to make it positive and divide through by the r and get dq dt equals, we brought it over there, divided by r is q over rc is minus q over rc plus the EMF over r. So now we just got to go through and solve that.